Okay, so besides looking at absorption and emission spectra, we can also take a look at the trend in ionization energy across a period to discuss the idea of electrons existing in energy levels and subshells. So as we go across the periodic table and removing an electron from an atom in a gaseous state, again, this X should be 1 plus, we can see that there's an increase in ionization energy as a general trend. This is because there's an equal number of inner shells causing shielding. And so as we get more protons, we get more attraction between those protons and electrons, a lower ease of removing electrons, and so more energy is required to remove the outermost electrons. What we're going to do now is we're going to take a look at the orbital diagrams of various elements and think about how these shells and subshells affect the ionization energy. So if we take a look at our first element, helium, I've highlighted the electron that we would have to remove to get that ionization energy in yellow. And in order for us to remove that electron, we have to go all the way from the first level away from the element to the energy level infinity. And so the ionization of helium is quite large because of that large distance we need to get and that large attraction. Taking a look now at beryllium, beryllium has 4 electrons. So now we're no longer in the first energy level. We're talking about the second energy level and the S sublevel. So we're taking a look at the one that we would have to remove is in yellow. And again, you can just see by looking at this diagram, there's a much shorter distance between the 2s and being removed versus the 1s. So our ionization of beryllium is a lot lower if we were comparing that to helium. Now let's take a look at boron. So when we're talking about boron, now we're talking about 5 electrons. So now we've moved to the 2p sublevel. And that's important. We're still in the second energy level, so it's still easier than removing from the first energy level, but 2p is actually even further away from the nucleus, so it experiences even less attraction. And so actually removing this electron is a little bit easier, so requires a little bit less energy than removing that electron from the 2s. So you'll notice when we're going from S to P sublevels, there's a little bit of a dip. The ionization energy doesn't follow that trend of increasing because those P orbitals are a little bit closer, and so there's a little bit of a decrease of energy required. Let's take a look at nitrogen now. So nitrogen has 3 electrons in the 2p that are all the same energy. These are called degenerate electrons. They all are at the same energy. So if we were to try to remove those guys, again, it would require more energy following our ionization trend. However, if you take a look at oxygen now, we're removing an electron from the 2p sublevel, but this time it's a paired electron. This time it has 2 electrons in that one orbital. So it turns out that that also causes a dip in the amount of energy required because of the electron-electron repulsion. So when we have those 2 electrons that are paired together, those electrons are not very stable, they're not very energetically favorable, being 2 negatively charged things in close proximity. And so removing that electron from that electron pair in that orbital is actually requires less energy than just removing a 2p electron that's unpaired. And so again, you'll see a little dip there that refers to electron-electron repulsion. Now taking a look at successive ionization energy. So instead of just one element losing one electron, we have one element that loses several electrons. Losing one electron is the first ionization energy, losing 2 is the second, losing 3 is the third. Let's take a look at what happens when we do that with aluminum. So the electrons that will be lost are highlighted in each of these cases. We have our first ionization energy, and again, we can sort of think about how much energy it requires to remove that one electron. It's the furthest electron away from the nucleus, so it requires the least amount of energy. If we take a look at the next electrons, we have 2 degenerate electrons in the 3s orbital. They require a little bit more. They're more close to the nucleus. Taking a look at the third energy, ionization energy, we require even more ionization energy. And then if we were to look at the fourth ionization energy, it would be completely off the charts. It would be greater than 10,000 kilojoules per mole because we would no longer be in that third energy level. We would be in the second one, which is much further down, much closer to the protons, experiences a much greater attraction. Now on this next graph, I've graphed all 13 ionization energies of aluminum, and there's some important details that you need to recognize. Along my scale, instead of having a linear scale, we have what is known as a logarithmic scale. So each of those jumps are times 10. Now I've mapped out my first, second, and third ionization energies on my scale. They're in red, yellow, and green. And you'll notice that there's quite a large difference between my third and my fourth ionization energy. And that's because, just like mentioned before, we're switching from removing from the third energy level to the second energy level. And so it requires a lot more energy. Moving further along the graph, you can see that we have our six um, electrons that are in the 2p sublevel, and then our 2 electrons in the 2s sublevel, and then you'll notice another large jump. That large jump, you've probably guessed it, is when we're switching from the second energy level to the first energy level. And so again, we can use these sort of jumps in ionization energy, as well as those little exceptions that we saw in the previous graph, to explain the idea of electrons existing in shells and sublevels.